Hello, dear students. So previously we have covered the relations and functions lecture third, and we have seen that what are the types of relation in first lecture, and then we have seen what are functions, types of functions, and invertible function, and what is composition of function. Now, in this lecture, we will continue our previous discussion and try to solve some questions also. So let's start and see that what are the examples given in your NCERT. So let's see the example number 24. What is saying? Let's start. So it is given that let Y is a set which contains elements like n square, where n belongs to natural number and it is a subset of your natural number also. So consider f. F is a function that is from natural number to y. Y is given as like this. F is a function which is mapped from n to y as fn is equal to n square. So fn is here equal to n square. And the definition of function is like fn. N is any natural number here inside the like this. N belongs to natural number and it is given as n square. Show that f is invertible, find the inverse of f. So we have to show that f is invertible and we have to find inverse of f also. So solution, we have given that we have to take an arbitrary y in capital Y. Suppose that we have taken any y element in capital Y, it is of the form n square. It is obvious that it will be is of the form n square because definition of y is like n square is the element inside it. Okay, and for like this is the definition for this y, and for some n belong to capital N, and a small n is any element inside like this natural number belonging to natural number, and for that a y is defined as n square. So this implies that n is equal to root y. So it means that for any n, the relation will be like root to y. Why? Because it is given that that n square is the relation for every n belonging to capital N. So if I take an any element y, and it's obvious that n will be equal to root y because n square is the relation. So if this gives the function g that is y belonging to n. So this gives me any relation that is or function that is y belonging y to n. Okay, defined by gy is equal to y root y. For this y, we have generated another function that is gy equal to root y. So now find out the g of f to n. So that will be equal to g of n square. Why? Because g of f or g of n is equal to g of fn that we have already told you. And fn value is what? If you take an fn here, fn is n square, so g of n square. Okay, so that will become g of n square, and g. Suppose we have put like n square in place of y, it will become root of n square. So it will come out to be n. Okay, and if I found here f of g, then it will be equal to f of gx and g f of gy. Sorry, f of g f o g y. If I find out, it will be equal to f of like g of y, and g of y is root y. So f of root y will be equal to root y square because definition of fy is like n square. So root y square will be there and it will come out to be equal to y. And we show that GOF is equal to IN. That is identity function from GOF to it is identity function from n natural number. And FOG is also is coming out to be like identity function in inside y. So this implies that f is invertible with f inverse is equal to g. F inverse is here equal to g. Okay. So we have generated another function g that is inverse of f. So that is the method to find out any function is invertible or not, that we have to find g of GOF of that function and FOG of that function. If GOF is coming out to be equal to IN and IX and FOG is coming to equal to IY, then F is invertible with F inverse equal to G. Okay. Now we will see another question of this, like another example. Let I clear it. So yes, the example 25 is telling us that let F, that is a function from natural number to real number, is a, and it is defined as fx is equal to 4x square plus 12x plus 15. So that F from natural number to any s, where s is the range of f, is invertible and the inverse of f. Okay. So we have to find out this function, that whether it is invertible or not. So let y will be an arbitrary element of range f. Okay. If y is any arbitrary element of a function f, then y will be equal to what? 4x square plus 12x plus 15, because fx is only the value of range of this function. So y will be equal to 4x square plus 12x plus 15 here. Okay. That will be equal to y for some x belonging to n. This is x belongs to natural number, and this implies that y is equal to 2x. If I do the perfect square here, so y will be equal to what? 2x plus 3 whole square plus 6. If you expand it, you will get this. Okay. And which gives us what? X is equal to root of y minus 6, y minus minus 3 upon 2. This will be the value of x if we find out here. And as y is greater than equal to 6. So y should be here greater than equal to 6, because we have the value under root, like this is under square root. So y minus 6 should be greater than equal to 0. If it is negative, then it will not be your valid function, because any number inside square root must be greater than equal to 0 if it is on numerator. Any number like if you have root minus 1, then it is not a valid number. Okay, it is a imaginary number. We are dealing here with only real numbers. Okay. So here this condition will be like followed. Y is greater than equal to 6. Okay. So let's move further and see what is in the next page. Just a second. Yeah. Okay. So I have to remove this thing. Yeah. So let us define g, that is g as any function from s to n by gy is equal to root of y minus 6 minus 3 by 2. So here g of x is equal to g of fx, and we put the value of fx inside g, and it will come like this: g of 2x plus 3 whole square plus 6. Now I have to put this g of like this function. So gy I have defined like this. So I have to put these total value inside this y. So if I put inside this y, the function will simplify in this term, and it will come like x. So it is coming equal to I of n. Okay. And similarly, if I find out for g of y, so I have to put f of y, like f of g of y inside this. So I will get it like, if by simplifying, I will get it equal to y. So I am getting here ix and here getting iy, or I can say that g of g of is coming in, and fog is coming here is, because it is defined from s to n. So I have taken here is and in. Here it is in and it is is. This implies that f is invertible with f inverse g. So it is coming out here that f inverse is equal to g. Why? Because this is coming as identity element ix, and this is coming at identity function or element like ix and iy. Okay. So if the function like gofx and fogy are coming like ix or iy, so they will become a invertible functions. Okay. Let's move further and see the example 26. Okay, I have to just clear this drawing and move further. Now, example 26. What is this saying? Let's see out. Consider f is a function that is belonging from natural number to natural number, and g is also a function that is like mapped from n to n. And h is also a function which is mapped from natural number to real number, and it is defined as where fx is defined as 2x, gy is defined as 3y plus 4, and hz is defined as sin z for every x, y, and z in natural number, so that ho of g o f is equal to HOG of OF. Okay, so it is a complex question. So we will see that how it will come. The answer will come. So we have HOGOFX. First, we will solve the left hand side of this. So HOGOFX is equal to what? HOGOF of X. Okay, and it will come like H of G of Fx, because I have told you GOF is equal to G of Fx. So I will put in h of g of fx, and it will come like h of g of fx value is what? Fx is given as 2x. So it will come inside as 2x. Okay. So h of 2x is coming here. And when we put 2x inside g function, what is g function? G function is this. So if I put here, it will come like 3 into 2x plus 4. After simplifying it, what we will get? It will come as equal to h of 6x plus 4. Now h function is what? Sin z. The sin z, I have to put inside the value of z, I have to put this 6x plus 4. So sin 6x plus 4 will be the final output of HOGOF. Similarly, if I found out HOG of OFFX, so this is the right hand side of this function. So this is HOGOFOX. So it will come out as HOG, and OF of FX is coming as like this FX, because OFX is becoming FX here. Okay. So after simplifying HOG of FX value we will put here, that is equal to 2x, and now HOG will become H of G of 2x. Okay, because O is there, so it will become G of 2x. Now simplifying it, we will get H of 3 into 2x plus 4. It is coming out similar to this here. So the answer will be sine of 6x plus 4. And this is showing us, that the left hand side is equal to right hand side. So this result is true in general. Okay. So we have any theorem, that is if f is plotting or mapped from x to y, and g is mapped from y to z, and h is mapped from z to s, are functions, then HOGOF is equal to HOG of OF. So these we have to remember, but it is we can prove it. We don't have to remember so much long formulas, but yeah, we need to prove it, and we should know the method of proving it. Okay, so let's clear this. Now proof is also given here. You can see it once. I have told you with the example. Now it is proving here with the general formula. You can see, and if you have any doubt in this, you can comment in the chat box also. So let's move further and see what is the next point. Okay, I have to annotate it and see. The example 27 I will left for you, because it is like similar to other examples which I have told you further, in the previous lectures. Try to solve it and get the result. Okay. So here it is a theorem again, that is you must be you must know this theorem, that if f is from x to y and g is from y to z be two invertible functions, then g of is also invertible. If f of g and g f and g are invertible function, then g of is also invertible, with g of f inverse is equal to f inverse o g inverse. Like if you have g and f invertible, then g of f whole inverse is equal to f inverse o g inverse. Okay, And its proof is also given here, that if you take F inverse O G inverse of O and G O F, then it will come like this. F inverse O G inverse. OG is like you take here from OG, and OF by theorem 1 it is. And if you further simplify it, you will get F inverse O G inverse OG. Okay. And it will become identity, because inverse of like inverse OG is equal to IY. That is equal to IY. If you have studied that, it will become identity function. So F inverse O IY by definition of G inverse will come like IX. Okay. F inverse O Y I Y is equal to IX, because inverse of IY is IX. So that is why it will come as it is to it. I have shown it is that it will come as IX. So you can similarly show that GOF O F inverse O G inverse is equal to I Z. So this is the like proof of this theorem, and let's move further and see that what are the other examples of this. Okay, just a second. Yeah. So some example are also given here. You can solve it. It is easier. Example 28 is easier. So try to solve it and get the result. If you don't get the result, you can comment or ask in the private sessions also, or doubt sessions. You can arrange for you. Okay. Example 1.3. Okay, exercise 1.3. Sorry. So till now we have studied about the composition function and invertible function. So this is the exercise on the application of these functions and these theorems. So let's try to solve some examples or such exercise questions here. Okay. So let's clear the drawing here. Okay. So here, first question is very easy. I think that you can do it. I will take only the questions which are like of good level, and you must know that questions. Find G of A. This is also a easy one. And let's try to see that any question is like of good level. So I will solve like sixth question for you. Try to see it and solve by yourself after I tell you this question. To show that a function is minus 1 to 1, given like if the function f is from minus 1 to 1, minus 1 1 2, sorry, minus 1 1 to real number. This is the function f, and it is given by fx is equal to x upon x plus 2. Okay, the function definition is x upon x plus 1 2, x plus 2 is 1 1. I have to show that it is 1 1. Find the inverse of the function f, that is from minus 1 1 to range f. Okay, so I have to find the inverse also. So if the function is 1 1, what I have to show, like fx is given as x by x plus 2. Okay, so if fx1 equal to fx2, this implies that x1 is equal to x2. I have to show that if fx1 equal to fx2, then x1 is equal to x2. So put here x1 by x1 plus 2, that will be equal to x2 by x2 plus 2. Okay, I substituted x1 and x2 in the fx. Okay, so after simplifying it, what will you get? If x1 by x1 plus 2 is equal to x2 by x2 plus 2, so what we will get here? From here, what we will get? Okay, so simplify it like uh, see here that if you have x1 by x1 plus 2 is equal to x2 by x2 plus 2, then it is showing here that x1 should be equal to x2. Okay, why? Because x1 and x2 will come like this only. Okay, this term is and like similar to this term only. Okay, so x1 will be equal to x2 here. So this means that mm, here it is a 1 1 function. It is a 1 1 function. Okay, I hope that you got this step why it is a one function. And find the inverse of function like -1 to 1 to range f. Okay. So for range, I will assume it like y is equal to x by x plus 2. That is the function. So I have to find the x in terms of y. Okay. So if I like cross multiply here, then I will get yx plus 2y equal to x. Okay. So take x common from here. If you take x common here, what do you get? I will like 2y will be here, and x 1 minus y will be remaining here. So x will come out to be 2y by y 1 minus y. Okay. So that is the value of your inverse function, because you have found out the x in terms of y. Okay. So here this function is your inverse function, and x is equal to 2y by 1 minus y is the given function. And here for y is belonging to range of f, range of f. Okay, y is here belonging range of f. Range of f is what? This. Okay, range f. And like your domain will be what? Domain will be here what? Uh, if you see here, the domain will be like real number minus 1 will be not here, because y 1 will be not defined. So range r minus 1. That's it. That will be your domain. Okay. So this is the definition of here of inverse function for this function. Let's move to the next question and find out what are the other things in this exercise. Let's find out. Yes. So we will see that what is the question 7 is asking here. Okay. Yes. So fx is given here as 4x plus 3. Okay. So try to find out y equal to 4x plus 3 in terms of like your x. Okay. X is equal to what? Y minus 3 by 4. So let's define it like g of y. G of y is equal to what? Y minus 3 by 4. This is your function gy, and this is your function fx. Okay. Now just find out f of f(o)(g)x. Okay. So f(o)(g)x is what? F of g of x. Okay. So f is what? 4. And if you substitute inside this gx, so gx is what? Like if you substitute x here, so it will become x minus 3 by 4. Okay. And here plus 3 is already there. So it will come like x minus 3 plus 3. So it is coming to be equal to x, which is equal to ix. Okay. So f of ogx is coming out to be ix. Yeah. And if you find out here gofy, and what will come like that? So gofy is what? G of fy. And if I substitute fy inside the g, so g is what here? Y. And y inside y, I should place fy value. 4y plus 3. Okay. So 4y plus 3 is the value inside this. Minus 3 is there, and upon 4 is that. So it will come equal to y. That is equal to y. So here you have like f(o)(g)x is equal to ix, and f of and gofy is coming out to be equal to iy. That is the condition that is satisfied here. That is equal to identity function. and here it is also equal to identity function. If this is coming out to be equal to identity function, then we can say that f is your invertible function. So I have to prove that it is invertible. So f is invertible function here, hence proved. Hence proved. Okay. I hope you got this question. So this was the seventh question. Inverse of f. What is the inverse of f here? Just I have found out that this is the function that is inverse of f. So we can write it like this: g of y, y minus 3, or we can write it like in terms of x, that g x is equal to x minus 3 by 4. If I find out it in terms of x, and it is equal to x minus 3 by 4. Okay. So it is the inverse of f here. Seventh question we have done here. So similar question is like your eighth one also. I hope that you can solve it by yourself if you have seen this question till now. Let's move further for the next question. Yeah. So we will solve ninth question. It is a good one, and let's find out what is it asking. So we have consider a function. We have a function which is from positive real numbers to -5 to infinite. Like the domain is a real number, positive real number, and the range is -5 to infinite, and it is given by fx is equal to 9x square plus 6x minus 5. Okay. Show that f is invertible with f inverse y is equal to root y plus 6 minus 1 by 3. Okay. So that y equal to 9x square plus 6x plus minus 5. Okay, write it like this. Now, what you have to do, that just find out the value of x square in terms, like x value you should find out in terms of y. Okay. So how to do this? Just try to write it like 9x square plus 6x is equal to y plus 5. Okay. You can write it like this. And now also like write it like 9x square plus 6x minus y plus 5. Okay. Now if this function has to be like defined, so this the discriminant of this function should be greater than equal to 0, because if the function is like uh, if the function has roots like positive or greater than equal to 0, if the discount is greater than equal to 0, then only the value that is satisfying here, that x is here what? X is here belonging to real number, then it should satisfy that discount is greater than equal to 0. So for this function, x value should be greater than equal to 0, means x should be real number, x belonging to real number, so discount should be greater than equal to 0. That should be satisfied here. So try to find out the discount of this function. That will be equal to b square, that is 36 minus 4ac, 4 into 9 into minus of 5, so it will become plus y plus 5 is greater than equal to 0. This condition should be fulfilled here. And now what you will get from here, just find out. Okay. Yeah. Okay, so this is the like discriminant condition, but try to find out the x value from here with application of your like Sridharacharya formula. Different value we will find out in other example. So let's find out the value of x in terms of Sridharacharya formula. I hope that you are aware of this Sridharacharya formula. So x value will come like what? It will come as minus b. What is minus b here? 6. Okay. Minus b. Okay, minus 6 is there. Plus minus root over b square, that is equal to 36 minus 4ac. So it will come as 4 into 9, that is 36 into y plus 5. Okay, that will come like this. And upon 2a, that is equal to 80. Okay. After simplifying it, what you will get? Minus 6 upon 8, minus 6 upon 18 plus minus root of this 36 will come out if you come out it outside, then it will become 6, and here you are remaining with y plus 5 plus 1, that is equal to y plus 6. Okay. So yes. And now, if you take the values like you have two values minus 6 plus minus like 6 root y plus 6 upon 18, and if you simplify it, it will come like minus 1 plus minus root of y plus 6 by 18. Okay. Now here that if you take like negative value of this function, that minus 1 minus root of y plus 6 by 18, so what will it inform? That it will we said that if you like use minus 1 you take here, plus minus root like sorry, if you take your minus value, just a second. Yeah, if you take here minus value of y plus 6, so the minimum value of y plus 6 should be what? It should be 0. So it will come like minus 1 by 18. Okay, if I take here 0, so it will come minus 1 by 18, and it will like come out to be equal to point something minus of point of something. Okay, so that will coming out to be the your like value of what? X. But X is what? Positive real number only. So X is only positive real number, so I cannot take the Y value as like this negative value as here. I have to take positive value only. That is only satisfying for X, and it will give us the positive values of X. So neglecting the negative value, we will take the X value as root of Y plus 6 minus 1 by 3. So this is coming out to be your like X value. And if now you will define it like GY, a similar method is that we have seen in the previous question. Now you should find out here f of OGX and f like GOF of Y, and you will get here IX and here IY. That will show us that IX is equal to X, IX and IY are like invert. They are showing that the function is invertible because IX and IY are coming, so the function should be invertible. And the value of inverse is by root y plus 6 minus 1 upon 3. Okay, so I hope that you got these questions, and yeah, that is a necessary condition for these questions to be fulfilled. So I have taken today some questions for you, and I hope that these are helpful for you. So let's try to find out some other things in this exercise, and I will check that whether other questions are good or not for you. So till now, whatever I told you, that were like enough for you for this exercise. Other questions are, I hope that you can do them, because I have told you the like tough one questions, and other are like they are easier, and I hope that you can do them by yourselves. Yeah. Well, let's move further, and the next topic is binary operations. It is not very important in your syllabus and for JE also, but it is like in your course that is of NCRT. So I will just wrap up in a faster way, or I will not give so much time for this. So binary operation is what? If you have two numbers, two real numbers A, B, like that. So you have the like association with these numbers, like you can do operations for these numbers like for addition is there, subtraction is there, multiplication or division. Division you should remember that the divider should not be equal to 0. Dividend, okay, divisor should not be equal to 0. That is, to notice that only two numbers can be added or multiplied at a time. Okay, yes. So now let's see some example of this. Definition is given: a binary operation like star on a set A is function star A into A to A, we denote it by star AV or by A star B. Okay, so these are some definitions. So you must not remember these very much, because these are asked very rarely in boards also. Okay, So here plus minus into are all function binary for operations on like real numbers. You can see by yourself here that these are some binary operations. And here it is example 30 is given as show that subtraction and division are not binary operations on natural number. Okay. So if you have like subtraction is there for natural numbers. So a minus b is not a binary operation as the image of 3 5 under minus will be 3 minus 5. Okay, so if you have a natural number like 3 or 5, and if you take the difference of this, it will come like minus 2 and it will be not a natural number. So your binary operation should be like if you have a some real number to real number, then it should satisfy that the operation is coming a real number output. So here natural number to natural number, the binary operation is not fulfilling the condition of like subtraction and multiplication or division, sorry, not division and subtraction. It is not fulfilling because you will get fractions also here, so that will be not a natural number. So you have to be aware that n to n is not a binary operation for like subtraction and division. Okay. Now we will see some other examples of this. Show that star r to r cross r to r given by a plus 4b square is a binary operation. You can show this by yourself. If you take some values here, you will get a real number only. So that will be your this exercise question. Let's move further in this part. So some examples are also given in further in your book. You can see it and solve by yourself. These are not very important, but you can see it by yourself once you have checked it. You can ask us if you have any doubt. Okay. So yeah, some operations are there like commutative properties. If their commutative properties shows that if you have a plus b is equal to b plus a or a into b is equal to b into a, then it is showing a commutative law. Okay. So similarly, you have a binary operation a to a is said to be associative a cross a star b is into star c is equal to a star into b star c. You have already studied these in sets also. So I hope that you are aware of these points and you can solve it by yourself. Okay. Let's move further and see that what are the important things in this. So associative law is there and commutative law is there in the binary operations. Okay. Yeah. Some inverse functions are also there in the. So I hope that you can study this by yourself. If you have any doubt, you can comment. And here are some questions also in this, and these are like define a star b is equal to ab or a star b is equal to a minus b z minus, like this is integer minus z is integer showing integer. So you have to show that these properties are like this binary operations are valid or not. So you can solve it and see yourself by taking examples. Okay, and try to solve that whether it is satisfying or not. So I hope that you got all the points of whatever I told you in this chapter, and I have covered all the important things for you in the class 12th for boards and like your school exams. And for JE, we will see in the next sessions with some examples, and I will take some exercise questions in a separate class. I will take only question bank or in that class. So yeah, these are some miscellaneous examples that you can practice it, but these are not very important for your boards in terms of board exam. So yes, this is summary of this chapter. So we are now moving on to second chapter, that is inverse trigonometric functions. Okay. So just a minute, I am coming from like this. Yeah. Basically, I think that we have covered the first chapter is completed today. So uh, yeah. So inverse trigonometric function. It is also a very important chapter in your class and for class 12th, and this is second chapter of your class. So we will see this chapter we will cover in next lecture, because today we have completed your first chapter of maths. So I hope that you have been aware of whatever I told you in the first chapter, and the application of that chapter will be in this chapter also. And it is it is good that we should start it with a fresh day. And till now we have covered all the parts of relations and function, and you should see all the lectures of relation function. If you have any doubt in that chapter, you can like comment or ask for any doubt sessions or doubt classes. And if you want any private sessions or one-to-one sessions, you can comment also or ask for the same, and we will arrange you for that also. So till now, I hope that you like the session today. So we will like wrap up it. Thank you and have a good day.